All right, everyone, we are back and we are starting this new section on probabilistic discriminative models. So we're in this approach, we're going to be actually modeling the posterior distribution of a class given a data point directly, and that can have certain advantages that we're going to discuss. In this particular video, we're going to just cover the introductory sections of this chapter, going all the way, so talking about briefly about fixed basis functions, and then covering logistic regression, so just the basics of how that works, and that'll just take us up until iterative rated least squares. So we'll do this one next time. Okay, so let's get started. Okay, so for the two-class classification problem, we have seen the posterior probability of class C1 can be written as a logistic sigmoid, acting on a linear function of x for a wide choice of class conditional probability distribution, P of x given CK. Okay, so remember in this setting, we are in the generative approach. We are modeling what the distribution of data looks like if I tell you that it's coming from a specific class. Similarly, for the multi-class case, the posterior probability of class CK is given by a softmax transformation of a linear function of x, right? So what we did was we figured out what the probability of one class was in some unnormalized way, and then we just divided it by some probability of posterior probabilities for all of the classes, and that gave us a softmax function. For specific choices of the class conditional densities, we have used maximum likelihood to determine the parameters of the densities as well as the class priors, and then use Bayes' theorem to find the posterior class probabilities, right? So remember, we did that. We used maximum likelihood for the continuous, for the case of continuous data, and we found that, for example, if we were trying to assume that all the classes had the same covariance, then the maximum likelihood covariance was a weighted average of the class covariances, etc. Okay, now however, an alternative approach is to use the functional form of the generalized linear model explicitly and to determine its parameters directly by using maximum likelihood. Okay, so we're going to just kind of, and I think we'll discuss this. Yeah, very good. So we're going to basically just skip the whole notion of modeling these class conditional distributions and just model the posterior distributions that we care about. And we'll see there's an efficient algorithm for finding such solutions. Okay, the indirect approach to finding the parameters of a generalized linear model by fitting class conditional densities and class priors separately, and then applying Bayes' theorem, represents an example of generative modeling because we could take such a model and generate synthetic data by drawing values of x from the marginal distribution. So remember that the marginal distribution, well, what is that? So that's going to be P of x, and it's going to be sum over all of our classes of the prior of that class times P of x given CK. Now, because we know what these are, or that they're given, or we'll fit them, whatever it is, and we are modeling these class conditional distributions, then we can actually generate data from the marginal. We can just generate ourselves a new data set by using this to sample, basically. So we're going to, roll a dice according to the probabilities of the priors, pick a class, and then generate a data point from that class. So that's kind of why it becomes a generative approach. You can generate a copy of your data set, and that can be kind of a good way of testing whether your model of the different classes was adequate, whether your marginal distribution sampled from your model actually looks like your data. In the direct approach, we are maximizing a likelihood function defined through the conditional distribution P of CK given x, right? So notice, this is what is the probability? This is kind of what you care about. What is the probability of a class given data point? Well, instead of going through this step, and maybe you don't care about generating data, you just care about, like, is this a cat or not? I want to generate pictures of cats and dogs. I just want to know whether this image has a cat in it. Well, why not just model that directly? So that's what we're going to be doing, which represents a form of discriminative training. So you'll hear about this a lot, the generative versus the discriminative approach. So we're now talking about the discriminative approach. One advantage of the discriminative approach is that there will typically be fewer adaptive parameters to be determined. We'll see that in a second, actually, as we shall see shortly. It may also lead to improved predictive performance, particularly when the class conditional density, so this thing, assumptions give a poor approximation to the true distributions, right? So it might just be easier if all you care about is this, this classification. Easier and more efficient. Okay, so fixed basis functions. So this is just I think it's a point we might have already covered, that many of these algorithms you can actually just immediately, instead of just modeling x, why not model some feature, some feature of x, some function of x instead? And a lot of the algorithms and things just go through directly, but you get some additional power and some flexibility from being able to use feature these other basis functions. So we have considered classification models that work directly with the original input vector. However, all of the algorithms are equally applicable if we first make a fixed nonlinear transformation of the inputs using a vector of basis functions phi of x. Okay, so let's right, so that's important. The resulting decision boundaries will be linear in the feature space, right? So not necessarily in the original data space. Right? Okay. And these correspond to nonlinear decision boundaries in the original space as illustrated in figure 4.12. So we can talk about that figure in a second. Classes that are linearly separable in the feature space need not be linearly separable in the original observation space. Note that as in our discussion of linear models for regression, one of the basis functions is typically set to a constant. So the corresponding parameter value plays the role of a bias. For the remainder of this chapter, we shall include a fixed basis function transformation, as this will highlight some useful similarities to the regression models discussed in chapter 3. Okay, cool. So let's have a look at, yeah, this is pretty cool. So you guys can see, okay, check it out. Okay, so this is our, yeah, you guys can see a bit. That's basically all that's going on. So we've got some blue points and some red points, okay? And they're not linearly separable, right? Like if I draw a line anywhere, you can see that the blue and the red, there will always be some blue and red on the same side of the line. So what we can do is we can actually, instead of using these raw values of x, we can perform a transformation. And we're going to perform a transformation using two Gaussian basis functions. So one of the Gaussians, so feature 1 of x is going to be this one, and feature 2 of x, oops, you guys can't see that, so let me put it on this side. So this feature 1 of x is over here, and feature 2 of x is over here. And the way you're going to compute the values of those functions is you're just going to plug in, you're going to take your point x and plug it in through this Gaussian. So the number that's going to come out is going to be between 0 and 1, depending on how close you are in a radial sense to the center of the corresponding feature. So let's see what that does. So let's look at, so let's just look at the blue points, right? So we've got some over here and we've got some over there. Now what we should expect is that as far as feature 1 is concerned, so let's actually use some different colors. So we're going to use some different colors while we're here. So there is feature 2 of x. Okay, so as far as feature 1 is concerned, feature 1 is, and let's actually even, just to make our lives easier, we're going to there is feature 1, and feature 2 is this Gaussian, right here. Okay, great. Now, as far as feature 1 is concerned, these set of points, right? Well, so where are they? They're sitting right near the center of its Gaussian. So a bunch of these points should be set to the value 1. And then these guys are actually quite far out, so they should kind of get squished down to the value of, I guess it's actually more than 2 standard deviations, so they should be quite close to 0. And if we look at what we actually see, that's quite what we see. So basically, these points here have been mapped there. And then these points, you guys can still see these points up here, well, they're really far out relative to the center of this Gaussian. So all of these points, when you plug them into that Gaussian, it's going to give you the number that's going to come out is going to be very close to 0. So those guys have been sent here. Now when we look at feature 2, we see that, sorry, with the red points, we see that they're kind of intermediate, right? They're kind of like with, just around, one radius away from the center of feature 1. So their feature 1 values are going to be kind of intermediate, not quite as low as these guys, but still, pretty low, not quite as high as this group down here. Okay, so we expect that, these guys are going to, as far as feature 1 is concerned, going to be at some intermediate value, and indeed we see that, they are. Now, as far as feature 2 is concerned, Well, where's feature 2? So feature 2, well, they're kind of sitting at the center of feature 2, right? So as far as feature 2 is concerned, they should be sitting, right at the top, and indeed, that is kind of where they are sitting. So for feature 2, the red points are at the very top, whereas the blue points are kind of lower down. So in some sense, now that's kind of a, you use kind of radial basis function here that seems to focus on just pick out feature 2, and you use that as your feature rather than the raw feature values to actually find a separation now. So if we're effectively separating in this feature space the red points from the blue points, because relative to this central Gaussian, all the red points are very close. They're kind of bunched up, whereas to the center, whereas the blue points are really far out. So that's kind of what's allowed us to make this distinction. So it kind of gives you an example of a setting where things are separable in the feature space, but not separable in the original space, and why it might be useful to use these features. Okay, so that's what that was about. Yeah, okay, good. So for many problems of practical interest, there is significant overlap between the class conditional densities. So this means that a particular data point could have come from one class or the other class. This corresponds to a posterior probabilities which, for at least some values of x, are not 0 or 1. So it's not for sure one class or the other. In such cases, the optimal solution is obtained by modeling the posterior probabilities accurately and then applying standard decision theory, as we already talked about. Note that nonlinear transformations cannot remove such class overlap, right? So because you're going to be sending the same point to the same place. So if you decide that that x is the x is in one, if x is in kind of the overlap of two classes in the original data space, those two classes are going to be mapped to a corresponding. They're going to have a corresponding overlap in the feature space, and that point x, which belongs to which lives in that intersection, will also live in the intersection in that map space. So you can't remove class overlap, right? You can't have a setting where x belongs to x belongs to both classes in one, and then after the transformation, it only belongs to one of the classes. Indeed, they can increase the level of overlap or create overlap where none existed. So you can actually maybe squish things down. So you can have a setting where maybe some data points. For example, let's do a simple example of that. We're going to do kind of a trivial example where here's our points of class 1, here's our points of class 2, and these are two-dimensional points. And now we're just going to let's say our phi of x is just going to be x1. And let's say phi 1 of x and phi 2 of x is just going to be 0, for example, right? That's kind of a silly example, but you can square it if you want, whatever it is. But the main point is that because these two guys overlap on the x-dimensional space, then it will also overlap in this. So we've kind of increased the overlap between the two classes because of our poor choice of the features. So let's just make a highlight of that. So cannot remove such class overlap, and they can increase the level of overlap or create overlap where none existed. You should also be able to, I'm trying to think, you should also be able to decrease the overlap, never quite to 0, but you can imagine like maybe there's some overlap and then you do a transformation that kind of squishes that part of the space to kind of a very small amount while expanding the parts of the space where they don't overlap. Then it seems, at least intuitively, that you should be able to reduce the overlap. You will never get it to 0. Like there, if a point, if a point, is in this overlap, if a point, lives in there, then no matter kind of what you do to this space, it will kind of continue to live in wherever you map this, So let's say we end up kind of doing something like that. You do your transformation. Seems like you could reduce the space kind of smaller and smaller by stretching out. I mean, we could even do it maybe here, like provide a stretch that stretches space out a lot. The farther out you go, and so you would end up getting in the feature space. You would, as far as that's concerned, you would now have kind of quite limited quite limited overlap. But you certainly, these points, the intersection will always be in the intersection. So I think you can decrease things, you can increase things, but you can't remove the overlap entirely. So that's what I would say. However, suitable choice of nonlinearity can make the process of modeling the posterior probabilities easier. Right? So it's kind of like what we just showed, right? Like we wanted to determine the posterior probability of these classes, and if we just picked the right features, then those posterior probabilities were basically kind of linearly separable. We can decide what the probability of one class or the other by just doing a linear function of these transformed features. So picking your features correctly can make your life a lot easier. Okay, such fixed basis function models have important limitations, and these will be resolved in later chapters by allowing the basis functions themselves to adapt to the data. Notwithstanding these limitations, models with fixed nonlinear basis functions play an important role in applications, and a discussion of such models will introduce many of the key components needed for an understanding of their more complex counterparts. Okay, so let's just, great. So we've seen some, even with having them be fixed, we can kind of gain a lot of advantages, so let's kind of keep them along, and you'll start to see that we just have 5s showing up rather than x. Fantastic. Okay, so now let's, this might actually be a good place to stop. So why don't we actually just stop right here, and we'll pick up with logistic regression in the next video. Hope to see you there. Bye.